Good afternoon. I'm between us and coffee, but fortunately we're ahead of schedule, so I'm not going to try to waste time, but we'll see how it goes. What I want to talk about today is something that's emerged from the OFI project. We've talked before about the OFI project is sort of broken down according to interest groups or classes of users, if you prefer. And the classical OFI WIG part of it is focused on distributed and parallel computing, and the so-called data storage and data access part of it, or DSDA, is focused on everything related to, as the name says, data storage or data access. So what we're going to talk about today is emerging from the work that's going on in the DSDA work group at the moment. DSDA is, by design, 6 months to a year behind OFI WIG, so we're in the same spot that OFI WIG was, a year or more ago, which is to say we're understanding the environment, developing and collecting requirements. And what I'm going to talk about now is sort of coming out of that exploration into what the requirements would look like. And it was driven by this notion that we have that somehow or other NV or NVM is going to be a key player in this whole space here in terms of defining new APIs. So the questions that we started with were, in what ways does the emergence of a new technology like NVM impact the network stack? And it's going to obviously make some changes. We're not quite sure yet what those are, but we want to understand those. And specifically, what does that mean from an API perspective? Which is another way of saying, in what way does a consumer view NVM such that the API can reflect what the consumer needs to see with respect to NVM? So again, we're taking this sort of tops-down, consumer-oriented view of trying to define the API. And that's what do Fabric consumers need? That is the question that permutates everything that we're doing in OFI land. What does the consumer need? What does the user need? That's what's driving all of our thinking here. So to answer all of those questions, again, at the sort of requirements level, we really need to start to think a little bit about how NVM is used in a little bit more detail, which is where we're going here. We started out by defining a set of, defining the scope of this kind of exploration. And we broke it down into three basic areas. So use cases, NVM as a target of memory operations versus NVM as a target of I/O operations. And I'm going to harp on those two throughout the rest of this presentation because that's one thing that sort of really began to boil to the surface. It's funny when I talk to people about NVM and what it means from a network perspective, the answer I'm almost always gotten back in the past 6 or 9 months is, oh yeah, that's NVMe over F. That's not true. That's true from the I/O perspective. It's not true from a memory operations perspective. And that's what I'd like to sort of tease out in the next 15 or 20 minutes here. Locality is obviously important. So we want to talk about both a device attached to a local infrastructure of some sort, an I/O bus like PCIe or possibly a memory channel, and also remote device accessed over a network. Again, this was the scope that we started with. We're going to see pretty quickly that I'm going to pitch the local part overboard and say that from a network perspective, we don't much care about how NVM is accessed if it's local NVM. That is not to say that there are not impacts. There certainly are. NVM introduces some impacts to the way that the application accesses and uses it if it's local, but that turns out not to be a Fabric issue. I thought for a while it might be, in the sense that it would have been nice if the way that you access local NVM is identically equivalent to the way that you access network attached, but we're not quite to that point yet. And the third was user mode versus kernel mode. And one of the things that's sort of come out of this for me is that we may discover, again, the way that all this is partitioned in terms of these interest groups, and we sort of artificially put all of this NVM stuff in this DSDA work group. It may well turn out that some of that winds up back in OFI WIG. So this is an artificial partitioning I created because my simple mind works in kind of rigid, structured sort of ways. If it turns out we need to move part of this back into the OFI WIG working group for further development, we'll do so. All right. So why am I making a big deal about this distinction between I/O and memory? It took a while for this to sink through my brains, but others are probably pretty far ahead of me in thinking about this. But when I think about I/O, I think about an extent of data, or a block of data, if you will, that's being moved to some abstract location where the abstract location is defined by something like a logical block address. And the key here is that what we're really talking about is moving a bunch of data from memory, the CPU memory, to some storage device. Now, it gets a little dicey with the advent of NVM because that storage device could itself be memory, or it could look like memory. So this is why the question about does this belong in the OFIWIG group or belong in the DSDA group is a little open-ended yet. But the fundamental distinction there is the way that, from an application perspective, he views the operation. In the one case, it's a block of data. Not to say that you can't do blocks of data if it's a memory operation, but it's a block of data moving to a storage device somewhere. Contrast that with a memory operation, which I kind of, callously describe as a load store operation, where what you're really doing is moving data between a CPU or an ALU register, if you will, and a memory location somewhere. It's a fundamentally different model from the perspective of the consumer. And I think we often sort of forget about that. I know I do, sort of forget about that. So I wanted to make that clear distinction because I think it's going to reflect itself at the end of the day in the way that the API winds up being constructed. So let me talk a little bit about what the transaction model means from both an I/O perspective and a memory operation perspective. We pretty much know, I think, and all understand in this room, what the transaction model for an I/O operation looks like. Generally speaking, in today's world, it's a client-server kind of a model, where a client sitting on a host somewhere requests service from a storage server somewhere, which services that request. He sends a request, and the server executes whatever operations are needed. And then the important point is he synchronizes at the end, the server does, by sending back some kind of an ending status or an ending notification. That's how the client establishes synchronization with the server. He gets the response back, and the client now knows that his data is happily stored somewhere else and he's good with it. That is not the same at all as what happens in a memory operation, where there is no server that you're talking to. There's just a memory subsystem or a memory controller. In that case, the thing that passes for what I'll call completion amounts to an acknowledgement that comes back from the memory controller that says the write's completed. More to the point, an I/O operation, because historically it's a long-lived operation, is sort of by definition asynchronous. So you want to send the request to the server, go away, wait till you get your completion, come back, and you don't stall the application, you don't stall the CPU at all. In the case of memory, you're not going away, you're sitting there waiting for the memory operation to complete, and everything stops until it does. Memory, of course, is going fast enough now that you don't stall, which is the objective. But there's a fundamental difference there in the way that the acknowledgement or the synchronization, if you will, comes back. So there's a pretty big difference from the application's perspective. And again, I think this is going to try to end up driving a lot about the way we think about APIs going forward. So let me just quickly review the use case for storage. This is a pretty familiar sort of looking picture. There's a client on the left-hand side. The fact that there's memory attached to a memory controller isn't really relevant for this picture. What's happening here is a client is trying to do an operation across a wire to some kind of a shared I/O device or a storage server or what have you. The fact that there happens to be NVM inside that storage server, for our purposes here, is irrelevant. What you're doing is you're executing a block protocol of some sort, or maybe a file protocol over a wire, and then that server executes whatever the storage operation happens to be. If he's doing it on NVM, so be it. If he's doing it on rotating media, so be it. But there's no real impact to the client of the fact that that data is stored on non-volatile memory in the server. So there's no real impact from the wire API perspective here yet. Let me talk a little bit about what the stack that we have today looks like that does that. At the top, I've shown a kernel application. Then there's some kind of a layer, a block storage layer, like a VFS kind of thing, which I've described as the access method, underneath which there's an upper layer protocol, and then a wire underneath that executes that protocol. And this thing I've been talking about, synchronization, in the case of an I/O operation, occurs at that access method or upper layer protocol layer. So it's the acknowledgement or the synchronization or the completion is really a function of the client talking to the server, if you will. It's built into the I/O protocol itself. And for those who are looking carefully at this picture, you notice that I've shown iSCSI as being on the same level as SRP or ICER, and that's not the case at all. Obviously, SRP and ICER are protocols underneath iSCSI. So the completion that I'm talking about here, the synchronization, is at the SCSI layer, not at the SRP or ICER layer, for those who are reading the slide very carefully. Something that we've talked about a little bit, there are a couple of problems with the existing stack model that we have today with respect to the existing networks. We talked about whether it makes good sense to do this over, say, sockets or iSCSI, and there's some problems with that were mentioned yesterday in the talk that Scott actually gave on behalf of Stan Smith and others. That fundamentally reliable socket semantics don't map especially well to a reliable messaging operation. On the other hand, the Q-pair abstraction works extremely well in the case of messaging operations, but it may not extend as well as we would like it to emerging fabrics in the future. Let me talk about that for just a minute, because this is a bit of a flashpoint, and it probably will continue to be as we debate this for the next year or so. But it says there it assumes a Q-pair based fabric. Let me talk about what that means. From a verb's perspective, the verbs exports to the application, or whoever the consumer happens to be, in this case, a mid-layer like iSCSI, it exports an abstraction of a Q-pair. I mean, that's pretty obvious. We all understand that quite well. And that as an abstraction is just fine because most I/O operations are based on queuing models, and it makes perfectly good sense. Where we run into trouble is not the Q-pair or verbs abstraction. It's the fact that verbs abstraction that's presented really is a representation of the hardware that's built into the underlying fabric itself. That's where we run into trouble. And it works fine with the fabrics that we have today, but the question becomes what happens when the next fabric emerges that does not contain that hardware representation of the queues that are represented so nicely by the Q-pair represented by verbs. That's where we're going to run into trouble, and that's where I think when we get around to having somebody actually illustrate this, we'll discover that building that Q-pair abstraction that doesn't exist in the hardware on top of some fabric that doesn't have that is going to be a problematic issue, which is why the question comes up about, if verbs winds up being the right abstraction going forward for all networks and all times. I want to be really clear about this. Verbs is exactly the right abstraction for those networks that it serves. There's no question about that, never going away. The question becomes what happens when the next level of fabric comes along. There's another issue related to that that we talked about before, which is if that's true, that verbs may or may not be the correct abstraction, every time we come up with a new wire or to some extent new features on that wire, we wind up impacting the upper layer protocols that access that wire. And that was illustrated yesterday in Scott's slides when he talked about LND, where LND is the network driver abstraction that lives underneath an LNet network. Every time we change the wire, what happens is we wind up changing the bottom edge, if you will, of that upper layer protocol like LND. We wind up generating a new LND, let's say. And right now there's several of them. There's one for verbs, there's one for Genie, there's one for sockets, at least the three that I know of. So don't think about this in terms of this K-fabric, and this is not a K-fabric talk, it just happens to be a convenient place to mention it. Don't think about this in terms of adding, K-fabric just because we think we can make things simpler. Think about it in terms of the next time a fabric comes along, we're gonna wind up spinning the ULPs anyway, like it or not. Why don't we just spin the ULPs one more time to work with a fabric which is abstract with respect to the underlying transport, with the hope that in the future we can fit more providers underneath a K-fabric transport without, again, impacting the upper layer protocols. So let me keep going here. I did want to talk just a little bit about what this local use case meant. So this is exactly the same picture, but I did say that the scope included both remote and local. So here's the local case here. And I've shown two forms of local, one being a well-known SSD that lives on a PCI bus, the other being an NVM device plugged into a memory channel slot called an NVDIMM, which exports a block-level interface of some sort. There are impacts on the way that the kernel accesses it, but it's not a network problem, so we won't talk about it in detail here. But for example, There's no notion built into the way that an application accesses local memory today of a flush into non-volatile memory. So as we begin to understand what it means for an application to access a block storage device plugged into a memory channel, we're going to have to integrate things like flushes, things of that nature that account for the fact that NVDIMM is fundamentally different from a classic DIMM. Again, that's out of scope for what we're talking about here, which is one of the observations that actually came out. It seems obvious, but it took a while to realize that it really wasn't an issue for the DSDA work group. Again, there was some thought for a while that it may be because you have that same issue on both sides of the wire that we would want an API that was similar. Turns out that's probably not going to be the case. So if you put the two together, this is what it looks like from a storage perspective. On the left-hand side is the local block I/O side. The right-hand side is the remote block or file I/O side. Doesn't have to be block. It could be file I/O or object I/O or any sort of I/O. It doesn't much matter. So I just put them together on one slide to sort of build the picture up. Just walking through quickly the left-hand side, just to be sure we're clear on this. There's the kernel application at the top, some sort of a block layer like a virtual file system, and then goes over a well-known PCI Express bus to an HBA talking to a classic SCSI device. That's the classic SCSI model of today. Moving to the right, there's this notion of NVMe, where NVMe is sort of the non-volatile version of a SCSI class driver, if you will, with apologies to Dave Minturn, but it's sort of the way I think of it. And typically today with an SSD, that's accessed over a PCI Express bus. But we're beginning to see cases where you'll have these NVDIMMs plugged into a memory channel as well. So that's just sort of the way that works today and the way we're going. I think we're pretty well established here and things are pretty well set with NVMe and the way that the NVMe model is working. And then we just talked through the stuff on the right, you know, the remote block storage part. The left-hand edge of that was the classic, you know, SCSI over a wire approach, which is ISER or SRP or something like that. iSCSI, or its RDMA implementations being ISER or SRP. Also includes things like NFS over RDMA and Lustre and so on. And I've shown where Kfabric would fit in here, where again, just to emphasize the point, the objective here is not to replace verbs. The objective is not to rewrite existing ULPs to the extent that we don't have to, just because of Kfabric. The intent here is to position ourselves for networks in the future that will take advantage of access methods that don't rely on a Q-pair sort of based architecture. All right, so let's move on to the persistent memory case. Now here's where things get interesting. So remember I made a big deal about the distinction between I/O, which we've just talked about, and memory operations. Now we're talking about what happens when you extend those memory operations over a wire, which if you think about it, that's exactly what remote persistent memory is doing. From the consumer's perspective, the guy on the left-hand side, he's going to want to access that non-volatile memory on the right-hand side, sometimes talked about as byte-addressable memory or something like that. As a normal memory operation, he's going to do a memory write, or in the vernacular, a put or a get, in mem terms, for example. So the consumer is going to really treat that like an access to a normal memory read or write. And somehow or other, we have to hide from him the fact that that access that he's doing is not local memory, it's over a fabric. Now, a couple of things might happen. If we had miraculously fast fabrics that could avoid the speed of light, then it would look just like a local memory operation and you wouldn't stall the process at all. It would just continue to run. We don't have that. We're not likely to have that tomorrow, though we may have it not distant future. But then there are other instances of that where you may wind up actually swapping the process out if that wire is long enough and slow enough, or you may just stall it for a little while. In either case, from the process's perspective, it's still going to look like a memory operation. The emphasis here in general is on single-ended operations for the simple reason that there is nothing at the other end with whom to do a two-sided operation. So there are going to be RDMA operations, you know, reads and writes directly to remote memory, one-sided operations. They may be synchronous or asynchronous, as I mentioned a minute ago. If this happened to be in local memory, they would clearly be synchronous because you wait for the result from the memory controller before you move on. The fact that we're talking about extending this over a wire means that things may stall, so they may become asynchronous operations. And the most important point I wanted to make here is that one at the bottom. Completions must comprehend the notion of a persistence domain. Somebody has to find a way to tell the consumer at the left-hand side of this picture that his data has been written to memory and is in the persistent domain. And that has to happen before he's going to move forward. He's going to want to know that his data has been stored and saved before he moves forward. By the way, I showed that thing down there. I invented something new, PM over F. I did that tongue-in-cheek just to make it clear that we're not talking about NVMe over F anymore. This is something totally different now. The whole point behind the distinction between I/O operations and memory operations. So what would that look like from a stack perspective? The interesting observation here is that there's no longer a ULP in the right-hand side. There is no server running on the right-hand side. There is nothing on the right-hand side that can communicate with the left-hand side to create a synchronization notion. There's nothing over there that can send back an ending status kind of a thing that says your operation is complete. It doesn't exist anymore. There's no ULP, but still, somebody has to do that. Somebody has to tell the local side that his write actually completed. Just to hammer the point home, the left-hand side here, the ladder diagram, is the way classic I/O works today. There's an I/O request that goes to a SCSI controller. The SCSI controller executes that request. Oh, by the way, is there a pointer on this thing? I'll bet there is. That wasn't the right one. I push that same button again? There we go.
Center black button.
Oh, okay, good. This dotted line here is the fabric acknowledgement. It is not the thing that says your operation is complete. It's the thing that says, I got your request. Then there's a number of operations driven by the server side, whether they're RDMA reads or writes is a function if you're doing a read or a write to the target. And then at the end, you get this ending status right here. I called it generically an I/O response. That's the synchronization point right there. This is when the consumer knows that his data has been written to disk. So that's the way I/O transactions work today. We don't have that luxury with I/O operations if they're extended over a wire today. Here's the read-write request, or a load store, if you will, over a wire, if such a thing exists. And then here's the wire acknowledging the fact that I got your data. It doesn't mean anything about whether it's in persistent memory or not. It just says that I received your request. So somehow or other, we have to create a synchronization point, which is the moral equivalent to this one here. And it can't be as simple as the NIC on the far side saying operation succeeded or operation accepted, request accepted. It's got to be something that says, not only did I get your data, I checked the CRC and I put it in the persistence domain for you. That's the challenge for us, and that's why the API for persistent memory is going to have to be different than the one for I/O. So just to hammer this point home again, if I haven't beaten it to death enough already, but in the case of traditional I/O, the synchronization occurs as a function of the interaction at the protocol layer itself, the I/O protocol layer itself. Again, there is no protocol in the case of a memory operation. That says that the synchronization is going to have to be a function of the network stack. So the network stack itself is going to have to say, got your data, it's in the persistence domain. A couple of ways you could do that. One is you could delay the wire acknowledgement that goes back, that say, until you've written the data into persistent memory, and then an acknowledgement is taken to mean, not only did I get your data, I'm the NIC on the other side, but I wrote your data into memory as well. There's other ways you could do this. You could add another protocol on top of it. You could add a second round trip, for example, such that the far side actually has some kind of a server function implemented in the provider here that returns an independent acknowledger. There's a number of ways that you could do it. The OFI architecture anticipates the fact that there are a number of ways that you can do it and allows that to happen. So that's something that we're talking about in OFI these days, how that completion is reflected back to indicate not only did data get there, but it's in the persistence domain. So here's the whole picture when you put it together. So that stuff on the left-hand side, we've talked about that. That's just the local stuff. And again, I'm more or less ignoring it because it's not wire-related stuff. Although I will say that I did extend it a little bit to show the notion of byte-addressable memory at the local side, in addition to I/O accesses that happen to be in a memory slot. I don't know much about that, so I'm not going to say anything about it because I'll say things that aren't true. And then I've shown here the classic sort of SCSI stack or I/O stack that we're used to, a SCSI Ethernet stack here, and then an RDMA accelerated stack here. And then I showed KFabric and what the role of KFabric may be in being able to shield the ULPs from future enhancements to the fabric, given that we're going to have to spin them anyway the next time a new fabric comes along, which it's about to do. And then I've showed here the case of byte-addressable memory, which I believe is going to wind up being a libfabric problem, because I don't think that there are any kernel applications that I can think of that are going to do byte-level accesses. So this completion problem that I was just talking about, I think is going to wind up being not a KFabric issue, but a libfabric issue. Again, just to remember, libfabric is the user mode library that's emerged for data storage and for distributed and parallel computing. So I think that that may be the guy that's most interested in being able to access persistent memory, remote persistent memory. I'm thinking now about PGAS and SHMEM, or maybe log updates would be another good example, where there's a client that would really like to update a remote shared persistent memory. That's what we're talking about there. So that's kind of what the possible I/O stack might look like going forward. We'll see, we can talk about this in another 2 or 3 years and see how good my prognostication about the future turns out to have been. So a couple takeaways, just to hammer home for one last time the points I've been trying to make here. We should focus on both remote I/O and remote memory use cases. There will be some impacts on remote I/O, but they're not as significant as you might think, because it's still the same essential transaction model. Not the same case at all for remote memory cases. So on the I/O side, as new fabrics emerge, we will have to adjust existing ULPs to account for those new fabrics to the extent that they do not fit well in a verbs infrastructure, which I'm told they probably won't. So we're going to have to deal with new fabrics emerging and the changes to the ULP. The point is, let's make those changes just one more time, not 20 times, 20 more times. And we need to anticipate the consumer's need to support them. So what's that going to actually look like? Then from the memory side, again, this is the thing that's most interesting. Remote persistent memory has unique transactional requirements, and they will impact the design of the API, like it or not. So from the OFI perspective, there's really two things we're doing. One is we wanted to deal with emerging technologies. That's what this says right here. An emerging technology is changing the way that we look at the Fabric API. And we wanted to be able to deal with the fact we wanted to be transport independent. And that's what's going on right here. So that's what I have to say. Comments, thoughts, suggestions, questions? Tom, I'm shocked. Okay.
I have a question. So you said the acknowledgement has to comprehend the persistence domain on the remote node.
Actually, what I said, to be really precise, is somehow or other you have to synchronize. And an acknowledgement is one good way to do it.
Right, but the ACK is only when the data has reached the persistence domain.
That would be the way you would implement it, yes.
Okay. So do you have a definition for that?
Definition meaning?
For an NVDIM, what would that be?
Well, from an NVDIM perspective, yeah, it's however it's implemented on the remote side. What is the definition of persistence domain is one question. How you actually do it, one of the things I like about this whole OFI project and the OFI architecture that Sean blessed us with is that there's a clear distinction between the API here and how you implement it here in the provider. That's what I'm trying to hint at. The way that you choose to carry that acknowledge back is a function of the provider, and the provider is a function of the wire that it's written for. So there's a number of ways that it could be done. I talked about a couple of them. And it's not, I don't think it's within the realm of OFI to define what that acknowledgement mechanism is. It falls to the provider to do so. Key is, from the user's perspective, he knows the same thing. He got synchronized. However that happened under the covers doesn't impact him one way or another. Did that help or confuse?
No, that helps.
Good. Then I failed because I was trying really hard to confuse you. Anything else? We should have coffee then. Thank you.